Welcome to the fourth in the series of signal analysis basics. We're talking today about the LTI, which is the linear time invariant system, and the game. I'll introduce the game a bit later, but let's just jump right into it. So what is an LTI? An LTI is a linear time invariant system. It is a system that accepts inputs and gives them out and gives outputs that are linear and time invariant. Linear and as we go on, I'll discuss the meanings of linear and time invariant. So let's draw up what an LTI would look like. This is a very basic block diagram of a linear system. We have an input and an output, and I'll give on the sides the reasons why we're getting such an output. So start off with a very simple input. Say for example you have an input of an impulse function to your LTI. One good example of this would be hitting a nail with a hammer. When you hit a nail with a hammer, you provide an impulse, and the response of hitting the nail with a hammer is that it drives the hammer into whatever material it is, wood, for example. So if you hit a nail with a hammer into wood, it will drive the nail into the wood. So if you provide an impulse function into the LTI, we're expected to get an impulse response out of the LTI. And this is something that is given to us because that's what we expect from it. So now what if we add some more to that input? So right now we're given an impulse function, but what if we delay the impulse function by a certain amount of time? Well, if we do that, then the output, the impulse response, will also be delayed by a certain amount of time. And this is what time invariance means. It means that if I hit the nail with a hammer today, right now, I expect it to go into the wood today. And if I hit it in 20 minutes, then I expect it to go into the wood in 20 minutes. Not right now and not far into the future. So time invariance means that if I delay the input by a certain amount of time, the output will also be delayed by the same factor of time. Next is proportionality. So let's add some more to our input. We have added the input. Now we've delayed the input by a certain amount. Now we are multiplying the input we're scaling the input, giving the input some amount of proportion with this function x of lambda. So we expect the output to be scaled by the same function, by the same factor x of lambda. So that's our proportionality. And last of all is superposition. If I do summation over all possible values of lambda in this case for our previous input, then I expect to do a summation of all possible values over lambda in our output as well. I made a mistake in the input. Sorry about that. In the output, sorry. This should be an impulse response right here. So a little bit of a notes on the side. We can call this input on the left side our input x of t. X of t just defines the function, and our output, funnily enough, because of the way that the LTI works, actually ends up being convolution. This is the base formula for convolution. If we put proportionality and superposition together, we get linearity. This is the same as this is the same as multiplying a variable a by 2, and you expect to get, let me rephrase that. If I have a variable expression a is equal to b, and I multiply the expression a by 2, I expect to multiply the expression b by 2 as well. That's proportionality. But if I sum up the values of a over bi, where I goes to n, then I expect to do that for b as well, where I goes to n. And that's our superposition. Putting those two together, that gives us linearity, which is why we can call these sorts of examples linear algebra, not just normal algebra. So let's move on. If we haven't, let's put in a new input of our own. Let's have our new input equal to e to the j2 pi f t, where x of t is equal to e to the j2 pi f t. So when we put it into our LTI, we will multiply our input with the delta function. So our input will now be the integral from negative infinity to positive infinity of our function x of L, so x of lambda, sorry, so e to the j2 pi f lambda times delta t minus lambda d lambda. And if you're wondering why we're doing it with lambda instead of t, if you look back on our board over here, we had reached a point where we had decided that x of t gives us a certain equation, this equation down here. So that is why we are doing that. Our output then will look very similar to the output in the other LTI. It will be the integral from negative infinity to the positive infinity of e to the j2 pi f lambda times the impulse response times h, the impulse response of t minus lambda d lambda. Now this is a convolution exercise, so let's change, instead of saying all of that we've just said, the integral blah 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 blah, let's say this is e to the j2 pi f lambda convolved with h of t minus lambda. And when we do that, we get through a process of some mathematics. All I've done here is just basic algebra. On this second step, you can see that there is something weird going on here, so I will explain what I did there. I let lambda equal to t minus u, or better yet, u equal to t minus lambda. So that, so so that when we do our derivative, du will be equal to negative d lambda. So that's what's going on here, and that's why we have negative right here. So we just put that together, and going further down one line, we split up the e terms into two, so that we can be able to keep two specific terms together. I want to have these two together so that I can make our next important term, this one, the capital H of u, which comes from the Laplace transform. That's outside the scope of this video, so you'll just have to take my word for it or read about the Laplace transform. Hopefully I'll get down to doing the Laplace transform in future videos. So this is what our input comes out to. On the left side over here, I have done the same operations with our inputs as I have done with the outputs, and I've come out to this being our input over here and our output being this thing over here. Now this whole operation of going through adding new inputs and trying new different inputs is actually called playing the game. In fact, if we go back over here, the game is actually trying out different inputs in an LTI system and seeing what comes out. Try it for yourself. Try any sort of periodical function that you'd like to put in and see what you get out of it, and you'll be surprised how much this works for. There's a lot it doesn't work for, but the ones that it works for are really useful and interesting. I hope to see you next time when we'll be talking about